I'm probably not going to use the slides. Okay. So I think last week we finished up moment of inertia, and this week we're going to continue in basically the first major topic, and that will be bending. And the reason why that's actually one of the major topics, together with torsion and shear, is because in any aircraft system, you can basically decompose the forces that act on the body into either a bending moment, a shear force, or a torsional moment, which is basically an in-plane moment. So if you look at basically on our aircraft, and we have some lift distribution going up here. This is the plane. Say we can basically decompose this force, and we can basically make a shear force diagram. Say it's quadratic, yep. And then we can get from the shear force, we can get a moment diagram. And this is linear. So this is quadratic. This will have some quadratic terms as well. So, and then we can basically, at any location at our, say, wind box or our wind, we can get some values, say V1, this is location V1, we can get moment 1, and if it's basically at a sweep angle, we can also get a torsional moment out of it, and then we can use these forces that we have, V1 and moment 1, we can plug that into our basically bending moment equations due to bending. We can put it down into our shear flow due to a force, and then we can basically get our stresses and superposition that, and then we can determine if it fails or not. So those basically are the three things that we can do. Like I said, we can always decompose our forces into shear force, moment, and torsional force. So we can basically, that will be the main topic of this lecture series, how we're dealing with these three cases. And for today, we're going to start with the first one, and that will be basically bending, and what bending does to our structure. So when we look at basically bending, see example. So let's take a bar, and we'll basically discretize it into X number of elements, and we'll try to bend it. So what we can say is, after bending, we'll see is this bar is deformed, of course, and then and we can make a couple of observations out of these two figures. This is basically before bending, and this is after. And we can say how the bending occurred. We can say, well, okay, this bending occurred because we had some moment forces acting on our body. And then if we look at it, we can make a couple of more assumptions or observations as what happens to these planes, basically these elements, and what happens before bending and after bending. So if we add basically an axis system, we can say that these planes before bending basically were straight and they did not basically deform. And we can make an assumption that after bending, so if we add again a plane to it, note that this time the plane is also deformed a bit, that locally this degree or this angle here remains 90 degrees. It's an assumption that we can make. And with that, we can make the assumption that after deformation, this angle is no longer 90 degrees. So we can make an assumption, and we can say after deformation, let's call our angle alpha remains 90 degree or does not. That's one assumption we can make. And it's actually, this assumption lays the foundation of two different theories. One of them says yes, they remain, and the other one says no. And the one that says it remains is known as the Euler beam theory. In this case, we say yes, alpha is 90 degrees before / after. And the other one is known as Timoshenko beam theory. And this one says basically the angle does not remain 90 degrees after deformation. So at first, what we say is this plane remains straight and at 90 degrees, so straight and perpendicular. So again, Euler. These planes that we looked at, so plane remains straight, straight line and perpendicular. Perpendicular states as minus 90 degrees, and Timoshenko says, well, they remain plane. Plane remains straight. A bit harder to read. Okay, doesn't go. Okay. Try to write a bit bigger. So the plane remains straight, but the angle basically rotates. So plane rotates a bit. So that means that this angle no longer is angle alpha is no longer 90 degrees. And we can, of course, if we make this assumption, if either sections remain plane and straight after, or they don't remain perpendicular, makes a huge difference on your basically derivations. And we can always come up with a conclusion of at what certain percentage we can take this into account, and we cannot neglect it. Often is when the beam is short and very thick, we cannot ignore it, and slender and long, we can ignore it. So similar to the thickness, the thick wall and thin wall, we can come up with a ratio of, if you remember again, where we said like thickness over height, this is basically less than 10%. 0.1, we can basically ignore it, and if it's a factor of just 2 or 3, then we cannot ignore it. We can come up with something similar to that. In that case, we just assumed it, like we said, well, we do a factor of 10. In this case, we can use a slightly bit more fundamental or scientific method to determine. And by just looking at, say, two things. So if Timoshenko doesn't, Timoshenko basically say it doesn't remain straight or perpendicular, sorry, and that's because of shear deformations. So if you take this into account, angle deformation, if we again look into our, say if you have a section and we have basically deformed it to the shear, then we said, well, it looks something like this, right? And this is the angle of the shear. This is shear angle. So this is basically what you're saying as well. So it remains straight, but it's rotated a bit. So you're basically ignoring shear, or you're not ignoring shear deformations. And with that said, we can use a small angle approximation. So we can say, if this is the real case, we can let's do a beam. We basically load it with a force, so we get our normal deflections, and then what we can get is also some shear deflection. This is our shear angle. So the deflection here due to shear, we can basically say we can use small angle approximations. So we can say this is length L. The deflection, say in W, due to shear is equal to the shear strain multiplied by or shear angle, which is equal to the shear strain, multiplied by our length. We know from shear strain that's equal to shear stress over G. And we know that stress as force, I'll go up actually. So WS, which is equal to shear stress over shear modulus multiplied by L. And shear stress is nothing than force over area. So let's assume that's a width W, B, and then a height H. Then it becomes the force P, let's call that, over H times B times G multiplied by L. So standard deflections, materials mechanics or mechanics of materials course, whatever it's called, we know by default that the deflection is given by PL cubed over 3EI, where E is our Young's modulus, I is our moment of inertia. From previous lecture, we know if we have a box section like a beam, that I is 1 over 12 H cubed B. So we can plug that in, and let's call this deflection bending. We have PL3, 12, so 12 over 3. Yep. H cubed B. 12 over 3 is nothing else than 4, so we can replace this by 4. And then we can make a similar assumption. We say like if 10% bigger or smaller, we can just make the same thing. So if these two deflections, if the deflection due to the shear contribution is less than 10% of the bending, we can ignore it. And if it's higher than 10%, then we cannot ignore it. So if we then do that, we can come up with a formulation that's dependent on basically the length and the thickness and the other properties. Yes?
So that essentially means that we could add the two deflections and that would end up with the total deflection.
Yeah, you can superpose this deflection and get a total deflection. Yes?
Where does the Young's modulus go for WB?
Oh, yeah. Like that. So we can make a similar assumption where we did the thickness over height. We say here again, the shear, deflection to the shear is less small than 0.1 to the deflection of bending. We can ignore it. And this assumption is also based on your guesses. So 10% is often the thing that we find acceptable. If you need very accurate, you can go to 5 to 10 for 5, 1, or even less. And then we can basically get this equality done. So we know on this side we have PL over BHG equal to 4 over 10 PL cubed HB E. So I incorporate that 0.1% or 0.1 factor, so 10%. We can get rid of PL on this side. We can get rid of P. This L becomes a squared. We can get out of BH. This B disappears and this one becomes a squared. And then we can basically get 4 over 10 on this side. So we get 2.5, so 5 over 2. And then we get multiplied by E over G. And then on this side, what we have is L over H squared. So now we have basically another dimension. We can just rewrite it a bit. L over H is equal to 5 over 2 E over G square root. And then we can say we can basically get our dimensions based on the thickness, the height of the beam, and the length, determine if we can ignore it, yes or no. In this case, for this lecture, for this bending theory, we will go for the fact that we can ignore it, that we say plane sections remain plane and straight before and after deformation. But this is basically the assumption behind it. And with that in mind, then we can go back to our deformed and undeformed sections, and we can define a couple of more variables that help us define the relationship between these two moments, M, and eventually the stresses, sigma. So the goal is find this relationship. So it's a function of our moment and probably some other variables as well. And that's the goal for this lecture. And to do so, we can look at one element before and after bending, and we can basically define a couple of more variables that we can use and points that are of interest. So if we look at one element, this is before, let's use, use this as the origin. This is z-axis. This is your y-axis. Then we have point N, point M, P, T, S, and things Q. And then we can do the same thing for after. Second deformed case. And we have the same thing, M, P, S, T, and Q. This is T, S, S, and this is our axis system. So in this case, the axis will be in the middle, but assuming that the cross section from the side is something like this, so it's bottom heavy. That means that in neutral, the centroid lies a bit toward the downside. Okay. So we can make a couple of assumptions or observations. First of all, we know since we deformed that M and P are shortened and N and Q are elongated. So observations, M, P, compressed, deformation. We get NQ elongated. And what we know is that even if we go through the thickness, we'll hit a moment that both sections are exactly the same. And in this case, we assume that's ST. So ST remains the same. And the later observation is important because this means that during the deformation, we can define an axis system that always remains the same in the cross section. And that's a bit dependent also on the geometry. And this ST is known basically as your neutral axis. As the name says itself, it's basically neutral, so it remains the same pre and post deformation. And we can make another observation is if this body is deformed, we can say that this deformation occurs or it looks like basically bending around a certain point with this given radius. Because if we would continue, we can basically say that this bending occurred as if someone would bend it around a given radius r. So if you basically bend it more, then this radius would be further closer. So we can say that as well. So we have a certain point that we basically where our bending is centered around. And once we define that, we can define basically also a couple of other coordinates. That's basically the distance towards it. We call this distance r. And what we call st, in this case we call that y. So we have our neutral axis lies at distance y above our centroidal axis in this case. And with that said, we can go ahead and define how the stresses and strain. Since we have a deformation, we want to have a look at the strains. So some parts elongated, some parts shortened. So we can look at how that is affected by it. So define. So this is r as well. This is theta. So that will be our deformation angle. So we can define that again. Let's assume we have small angle approximation. So small angle approximation basically says sine alpha is equal to alpha, tan alpha is equal to alpha, and cosine alpha is equal to 1. So we can use that as well. Let me actually pull out the figure a bit. So this is the figure on the slide number. So we're talking about this figure before and after. So if you want to take a look. Okay. With that said, we can basically look at what happens to the strain. So first of all, we can define the strain as the deformation over the original length. That's the original definition of a strain. And we can put that into terms what we see here in our section. So before the deformation, what we get is our original system. So we can say that r minus y And then we're looking at the variation of strain. So this is not theta, but it's that basically small percentage or small change in the strain angle. So we multiply that by delta theta. And if we looked at so another key point that we have to make, in the undeformed case, we have basically our ST and our neutral axis will coincide. So now that we have deformed, our neutral axis has shifted upwards. So our neutral axis in our original state was nothing else than the original length of rotation r multiplied by d theta. And then we divide that by its original length. And in that case, this will be also r multiplied by d theta or delta theta. Like I said, we use basically a small angle approximation. So the sine of alpha times r, that's the alpha deformed. And then we can basically write this as r d theta minus y d theta minus r d theta over r delta theta. So this drops, so what we get is minus y over r. So our strain is now defined as basically minus y over r. And then we have Hooke's law. From Hooke's law, we can go, we'll call that sigma is equal to E times epsilon. So now if we want to go to stresses, we basically multiply by the Young's modulus. So our stresses are minus y over r multiplied by E. And if you want to go from stress, note the key point was eventually going into definition of bending moment. So we want to go to moment, and how we define a moment, that's basically known as the integral from, in this case, the area of the stress multiplied by, in this case, the y distance, y, dA. So we can substitute these two can substitute the stress into our moment equation. And then we'll get is y squared a, get a minus here, take the minus out. And we know that the integral, this equation, the moment, stresses are independent of the area. It's not a function of x and y, so that's basically a constant. So we can rewrite it a bit. This, I'm missing the e. This later part, that's what we did basically last week. It's the moment of inertia, so we can substitute that. And then we basically get the equation that we want. So we can divide okay. So let me do one more step in between. So we have here, so this is correct. So moment over I, let's rewrite this. Is equal to this. And we can reuse definition here. So we can rewrite this part as sigma over E. I'm dropping a minus sign somewhere. I can rewrite this as sigma over Y is equal to E over R. Double check. Okay. This is this. We multiply this by. Okay. I made a mistake. So take this one. So we have the integral of a sigma y dy. This remains. So now we substitute our stresses, like here. So what we get is minus y squared over r e, integral of a dA. The integral of dA is only so the radius and e are not a function of the area. So that is e over r, and this was moment of inertia has given us the y squared dA. So this is where I comes in, and this is the negative sign remains. And now we can write this relationship as well. So we basically now rewrite E over R as equal to stress over Y. So we can substitute that back in, and we get that the moment is equal to the stresses multiplied by the moment of inertia over Y. And what we want to do is we want to get the stress as function of moments. So we just rewrite that and we get our final equation. We say that direct stresses are a function of the moment multiplied by the distance y over the moment of inertia I. And this is our final equation that gives us the relationship that we started off with, or that we wanted to derive. This gives us a function that stress is a function of our moment y and our moment of inertia. So now, as we have a given a moment, and we know our cross sections, we can determine where the stresses are due to that moment. And there's a couple of other things that this tells us. Let me just wipe this off. And we write out, to be exact, this is our equation. Now we know a couple of things. If this distance y is the distance from our centroid. M is our moment, applied moment. And I is moment. So we know that the applied moment doesn't change around at the location of our cross section. So it doesn't matter if we are at this location of our cross section or here, it doesn't change. The applied moment is the applied moment. The moment of inertia doesn't change with location of cross section, but changes with the shape of our cross section. So what we can say here is that our direct stresses, so sigma z, varies only with y. And we also know that this variation with y is linear, since we have a singular y in it. So what it has been in practicality. So if we have a certain cross section, we look at a given, say we have an say we have an I-beam, and we have given a moment applied to it. We determined that this I-beam, if we look at the stresses, the direct stresses, it will be something like this. In this case, it's double symmetric, so let's assume it's T. Then we get large stresses at the top and small stresses at the bottom. This will be the shape of our stress distribution in thickness direction. If it be symmetric, then we know that basically goes through our center. Actually, for a T section, we'll go like this, because this goes through the centroid. So in the case of a T section, it will be a CT, and this will be a CI. So we know immediately we can say something about our stresses. So of course, if you're an engineer, you want to evaluate the structure. Say if you have a material given, steel or aluminum, you know those materials have certain failure stresses. So if you want to know and evaluate your structure, so you don't want to evaluate at every point, but you want to evaluate it where the maximum is. So you know by definition, if you have a T section, and this is our centroid for our T section, for example. So we know from this formula that y is important. Then we know that at this location, y is basically max. So if you want to be an engineer, you want to be making sure you would evaluate it at a maximum location to get sigma max. It's a function of y max. Because the moment and then moment of inertia, those remain the same. If we look at the lecture slides, basically it also contains some slides on the moment of inertia, so I'll skip those because we basically used 2 lectures for that. And Einstein term and what the effects of thick walled versus thin walled. Okay. This is just now we can actually do this. Let me see. This is again an example regarding moment of inertia, but good to evaluate for stresses as well. So in this case, so you have these 2 examples, right? Okay, circle. Let's assume that the radius of the circle is basically the same as this dimension, the length, the height. So diameter and radius are the same. So D equals H for our assumption. Now, if we look at our stress equation, we have a couple of variables that we play with. In this case, if you want to look for the maximum, we say we're going to maximize y. Let's make it a symmetric cross section. So y is in the middle. So in this case, y is equal to r in this case, and y is equal to, say, h over 2. Which should equal r. So in this case, both of them are the same. So how do you determine which of these two structures will be more efficient in carrying bending? So the applied moment is the same. In this case, the moment of inertia will have an effect of it. So whenever we get moment of inertia of a circle versus moment of inertia of without the C beam. So in this case, if you want to be as an engineer, you want to determine which property is better, you will look only at the moment of inertia of the cross section. That will determine which cross section is the best. And then, of course, if this doesn't, say for example, in a fuselage, a circular cross section is always better, even though if it's, say, compared to a closed one. So in some cases, you will still get failure, while, say, in other cross section might not give you failure. But the circular section will give you other advantages. So you want to increase this moment of inertia. And that's what we said earlier. Last lecture is we can add stiffness to it, similar to just increasing the moment of inertia. So if we basically change, without changing our geometry, we can change the value of the moment of inertia by adding stiffness to it, and then we can basically get our stresses to go down since our moment of inertia value increases. And same thing for plates. And again, if you want to increase some moment of inertia terms we can use, or you want to decrease the stresses, we can either change the shape and get a higher moment of inertia. But if we are limited to our shape, then we have to increase our moment of inertia, and we can do that by adding more, say, Steiner terms to it, adding more stiffness to it. I think there's one example, 2 slides further. Let's do this quickly in class. So it's a thick walled I-beam section, and you have a given moment, and you have to come up with the stress distribution of that cross section. So dimensions is 20 millimeters, 25, and we have 200 and 300. So we know our equations, my Ixx. M is given as 100 kilonewton meter, right? Kilonewton meter. Now then, what's always useful to do, always convert to the same dimensions which moment of inertia is in, and your y, location y is in. So this becomes 110 to the power 3 kilonewton millimeter. So you just multiply by 3. And if you want to go in Newton millimeters, then this becomes 10 to the power 6 Newton millimeter. So the goal is to determine the moment of inertia, since that's only, say, difficult part in this case. And if we do that, in this case, you basically cannot ignore you cannot use the thin wall assumption. You have to go with the thick wall assumption. So you get 1 over 12 multiplied by 200 multiplied by 20 to the power 3 plus, that's basically this part, Steiner term. That's 200 times thickness, that's 20, multiplied by d squared. So that's basically from 10 to 150, so that's 140 squared. And you have two of these, plus the center web, that's 1/12. H is now 300 minus 20 minus 20, so that's 260 to the power of 3 multiplied by 25. Yeah, just multiply by 25. And then you get to the power of 4. 103 10 to the power of 6 millimeter to the power of 4. And now we can plug this in. So we had 110 to the power of 6 Newton millimeter. We divide that by 193.7 10 to the power of 6. And this is multiplied by y. So what we get is 0.52 y. So we get basically a function of our stress as function of our distance y. It also says a negative bending moment, so we have to apply a negative bending moment. So now we can basically plot it, as I said before. So we evaluate basically at one location. So we evaluate sigma at equal y is 150 plus minus 150. They're equal, but they're just opposite in sign. If you evaluate that, so 150, so we get 75, 74 approximately, slightly bit more, 76. Yeah. So we get 76 Newton millimeter, which is megapascal, millimeter squared, so which is 76 megapascals. And then you can draw it, if you would draw it, then you get something like this. So you know the maximum is 76. On this side, maximum is 76. Top is compression. So let's draw it like this. And this is tension, far away from the axis. And then get straight axis. So this is the center point. And then basically have all the stress distribution through the thickness. And it's important to say a couple of more things about it. So far, we only assumed one bending moment. And if you noticed, I went from I to IXX. So the reason for that is we only have looked in bending around basically one axis. And that's around your x-axis. And because you're looking at bending around the x-axis, that's for basically you need moment of inertia around x. So far, basically looked at a couple of things. Our cross sections were symmetric without specifically mentioning it. We had a single bending moment. So we're gonna keep this for same for now. But what happens if we basically get two bending moments? So we looked at how we derived it. So moments around x. You can basically do the same thing, but then moments around y. You can repeat the same derivation, and then what we get is, if you repeat the same derivations, you get moments. Let me get rid of this example here. So we get this, before we got moments x, y, ixx, and now we get moments around y-axis multiplied by the x-coordinate, iyy. And if we have a moment, basically moment around two axes, or moment at an, say, at an angle. Say, for example, we have a beam C. So if you have given bending moment on one axis, but your structure is basically transformed or rotated by an angle alpha. So what we can do is we can decompose this moment, just like forces you can decompose, into a component, a new x-axis and a new y-axis. And now you basically have to deal with a component in x and a component in y. So if you want to have a combined section, what we can do is just superposition the two, they're independent of each other, and our new stresses become mx by y, ixx, plus the moment around y multiplied by x, iyy. And there's one example in the lectures, basically deals with this problem. I think it's slide 6, 12, 18, 24, 25, 26, 27. So it's on slide 27. We don't have any time more for this lecture, but do that at home, and then we kickstart the next lecture by going through that solution procedure. Solutions are online as well, but just skip to the slide, don't look at the solutions, and then we can look at how that basically affects it. And then for next lecture, what we're going to go is we're going to tackle the first assumption, this one, and we're going to see what happens when we have non-symmetric cross sections. Okay. All right. Thank you. I'll see you guys next day.